Good morning. So midterm 2, it's coming right up in just a couple days here. So let's go ahead and review. Let's take a look at some of these practice problems. So I hope you guys have been looking at some of these and trying them out. In fact, it'd be great if you've already looked at all of them. And then we can just talk about some of the setup and try and reinforce many of the concepts. So the first problem on here, I'm going to start with this set of 4 problems, and this was a midterm exam that was given probably a few years ago. So this does date back a ways. But the first problem it talks about is, it's talking about these particles decaying into other particles, and it's a kaon decaying into a muon and neutrino. Now the numbers that are given there, the 494, 105, and 0, those are the masses. Those are the MC squared values. And what we're supposed to calculate are the total energies, kinetic energies, momentum, velocity for the decay particles. Now we know how to do this. We've derived formulas in chapter 36 using relativity to solve for all of these quantities. And so in part B it's saying once you get finished, show that energy and momentum have been conserved in the reaction. Now when we derive those formulas, energy and momentum conservation is actually what we started from. So part B is just kind of a check. It's saying go back, check, see if your results are consistent with what we would expect. Now here is what the key looks like for problem 1. Actually problem 2 is on here also. So here is problem 1, and here is that kaon that we're starting with, and here are the 2 particles that it's decaying into. Now did it say, it didn't say charges. So I went with positive charges for some reason. All these particles could be, these 2 particles could be negatively charged too. It'd be essentially the same reaction. So I've written down the masses. Now I'm using that shortcut method that we talked about and we've used in class, of where M by itself represents MC squared. It just saves me from doing a lot of extra writing. So again, if you don't want to use that method, that's fine, but plan on spending a little more time writing down all the symbols. If you do practice this and you get more familiar with it, once you're familiar with using these shortened versions, you can save some time. So anyway, those are the masses that we're starting with. Our formulas that we've worked from, some of the formulas involve Q. Now I went ahead and calculated Q as the mass that goes missing. So, one of the features of special relativity is we find out, well, mass isn't really conserved. And in many reactions, it's not even close. A lot of mass gets converted into kinetic energy. So I went ahead and calculated Q just as a way to see how much of the original mass, which was 494 MeV, how much of that is actually going to disappear and show up as kinetic energy. So 389, that's a sizable portion. Now I went back and I just used formulas that we had derived, and notice the problem did not tell me I had to derive the formula, so I'm going to go ahead and use this formula that we've worked from before. And plugging the masses in, getting all the masses straight. One of them 0, so that's just going to zero out parts of these formulas. I ended up with almost evenly balanced energy, so that's kind of interesting. The muon ended up with, just kind of coincidentally, 258 MeV, and the neutrino at 234 MeV. Now those 2 should add up to 494, and actually that's what we're saying here in part B. That's an energy check. So energy should be conserved in the reaction, and what that means is the energy we start with, which is MC squared for the kaon, needs to be equal to the total energy of the 2 decay particles. All right, Now, once we've got the total energies, we can get the kinetic energies a couple different ways. We derived formulas for those, or we could just take the total energies and subtract off the masses. Now, using this approach, I ended up with the kinetic energies, again, this time the neutrino has quite a bit more of the kinetic energy than the muon. Now, in this reaction, the muon has a much lower mass than the kaon, and that means that when there's a lot of energy being released, a sizable portion, it's going to tend that the kinetic energies are not so different, and they're not terribly different here. Now, they wanted the kinetic energies. They also wanted velocities and momentum. Now, momentum we can get, again, using formulas from special relativity. So this is this is all special relativity stuff we're looking at here. And when we calculate the momentum, look at that. The momentum values match up, and so on part B, I got to check that box and say, yes, I showed that the momentum was equal. Now, the two particles are going to be headed in exactly opposite directions. That's how the momentum will be conserved, but the amount of momentum will match. Now, as far as getting velocities, I went back and used gamma formulas. Now, for the neutrino, first of all, we're assuming the mass is so small that the gamma is effectively infinite and that the neutrino is traveling right at c. So you can write that as 1.00 c, certainly to a good approximation. I mean, in reality, there's a little bit of mass in the neutrino, and that means it's not quite traveling at c, but we haven't really taken that into consideration in the examples we've used with these neutrinos. Now, with the muon, I can get a gamma factor. The gamma factor is 2.46, and that gives me a velocity of 0.914 c. So these two decay particles are coming out at pretty high speeds. The muon's at 91% the speed of light. The neutrino is effectively at, the speed of light. It's 99.99999 with a lot of nines on it, the speed of light. All right, and so that's it. That's problem number one. And again, it's mostly special relativity, and it's specifically the energy and kinetic energy, momentum, velocity types of calculations. And those are all things that you want to be prepared for. Okay, moving on into problem two. Problem two says this. Now, it's worded a little funny, so let's ask what this means. If we had a 100-watt light source, and it says the wavelength of the light is 620 nanometers, so it's not an incandescent bulb, it's not radiating across the spectrum, it's 100 watts, but it's really just generating photons all with the same energy, all with the same wavelength to them, and it's located far, far away. So when we say this thing's on the moon, what we're really thinking of is if we took a light bulb and held it out in space at that distance, what it asks is how many of those photons from that light bulb would be reaching the Earth each second. Is there going to be a lot of photons reaching the Earth from that light bulb or not so many? It's a good distance, right? And the photons are going to radiate in all directions. Now, they've given us the radius of the Earth and the moon radius and the Earth-moon distance, and well, let's see how this sets up. So here's problem two, and what problem two is showing here is that we have a light bulb out in space somewhere at the distance of the moon, so 384,000 kilometers, and we're going to be here located on Earth and ask how many photons are going to be reaching Earth from that one light bulb sitting out in space far, far away. So we know from problem solving examples from chapter 37 and maybe 38 also, I'm trying to think, mostly 37, there's just a lot of photons being generated. even from something as simple as a 100-watt light bulb. So I took the 100 watts and wrote that as 100 joules per second. And then what I did was I found out just how much energy does each photon carry. And I used our favorite formula, hc over lambda, and it worked out, that's 1240 over a wavelength of 620. It worked out to be 2 eV. So these 620 nanometer photons have an energy of 2 eV for each photon. And so I did a units conversion into eV, and then I used the 2 eV number to calculate how many photons this would be. And what I came up with was this 100-watt light bulb is generating 3 times 10 to the 20th photons every second. And that's a really, really big number. So if these are being sent out into space uniformly in all directions, how many of them bump into Earth? So to find that out, I set that up as a fraction. What fraction of the total number of photons would reach Earth? Now, Earth creates a circular cross-section. So if I think of a sphere, so a spherical and imaginary sphere shell that exists at this distance, 384,000 kilometers, how much surface area would that shell have? And the surface area of the sphere is going to be 4 pi d squared. So of that total, 4 pi d squared, Earth only creates a cross-section of pi r squared, where r is the radius of the Earth. So I am using the radius of the Earth here. Now, as far as distance, let's see. I'm just thinking of the Earth as creating a circular cross-section. So I don't really need to, I can use the 384,000 number and kind of ignore the radius of the moon, and I can ignore the radius of the Earth as far as measuring distances. I just need to have the radius of the Earth to determine what that cross-sectional area will be. And so I ended up with this fraction, pi r squared over 4 pi d squared, and that turned out to be 1.72 10 to the minus 5, or 1 photon out of every 58,140. Okay, and you've noticed that I like kind of writing things like this often, you know, 1 out of this or 1 out of this, and you can do that on your calculator just by inverting that number. So the 58,140 is the inverse of 1.72 10 to the minus 5th. That's all it is. It's nothing fancy. So, you know, the portion of photons that are going to impact Earth is 1 out of every 58,140. So I put that in to find out of the total, the 3.13, 10 to the 20th, and that left a really big number. 5.37 10 to the 15th each section. Now, boy, it really didn't ask anything else. I can think of more questions we would want to follow up with. So for example, if instead of the entire Earth, what if we just put out a 1 square meter? What if we took a 1 square meter and pointed it so that, you know, cross-sectionally we have 1 square meter? How many photons would that create? And I guess we would have to go in and replace this pi r squared with 1 square meter and get an idea of how many photons we might be getting every second. That would be an interesting follow-up question to take a look at. Okay, and kind of estimate. I mean, r here is 6 times 10 to the 6th meters. This is a factor of pi, so 10 to the 6th, 10 to the 12th, a couple factors of 10 to the 14th maybe. Ooh, we might be getting down. That is an interesting question. I'll have to go and take a look at it. It might be down in the, you know, small numbers, maybe 5 or 10 or 50 photons hitting each square meter of Earth every second from this one light bulb. That's, you know, 384,000 kilometers away. So an interesting question to follow up on. All right, we've got questions 3 and 4 here also, so let's do those. 3 is comparing a photon, an electron, and a proton, where each of those 3 particles have been given a kinetic energy of 700 MeV. So, you know, if I have 3 particles, photon, electron, proton, they all have the same kinetic energy, what would the other properties be? How would they compare with each other? And again, the difference between these 3 are going to be the masses. So those values that are given here, I hope it's familiar enough now that you recognize those as the masses of the 3 particles. The photons are massless. The electrons come in at 511,000. I wrote that as keV. And the proton, 938.3 million, or mega eV. So let's take a look at this. So this problem is some combination of relativity and also quantum mechanics. So we're using stuff from chapters 36 and 37 to fill in this table of all the quantities. So let's take a look at that. So I'm going to write down the given information, and I'm going to organize everything in terms of, well, first of all, I'm going to list all of their MC squareds, and then I'm going to write down their kinetic energies, because I was given that information. And then what I'm looking for is this. You know, one of the real emphases that we've made in these chapters is that there's a set of general formulas that you can work from. You don't have to treat photons as being different from electrons or protons. You can use the same formulas for all of them. And so I'm going to do that. What I'm going to do is I'm going to look at that list of quantities that they want me to solve for, and I'm going to think in terms of what's a general formula that would apply to all of these particles. And so for total energy, I went back to, you know, one of the starting formulas that we learned back in special relativity, that the total energy is mc squared plus kinetic energy. Hey, I have both of those quantities. I can just add them together. Now, for photons, we find out that there's no mass, and so the total energy matches the kinetic energy value. That was easy enough. For the electron and the proton, however, I am going to have to, I'm going to go back and double check these numbers here. It is MeV, isn't it? So that is a lot of kinetic energy for a photon, and that is a lot of kinetic energy for an electron. Now, it's not so big for the proton, because the proton has a mass comparable, but that's a lot of kinetic energy to give. By saying that, what we're indicating is that the electron is going to be going really, really fast in this example, and the proton is certainly going to be going fast, but well, we'll see. We'll see by how much. Just kind of anticipating what the numbers might look like. So for the electron, I went ahead and added on that 0.511. It looks kind of silly. Don't worry about losing sig figs on these losing points because of sig figs on the problem, because it turns out that if you've got a calculator that can keep, you know, most calculators keep 9 or 10, 11, 12 significant digits all the way through, and that's enough to make these formulas work. And so I'm using this and plugging formulas in, and it's only really the proton that has a measurable difference, a really significant difference from 700. I also use the momentum formula. So I followed up with the momentum formula, and for photons, I know that the momentum and the energy and the kinetic energy are all the same numbers, but I could still imagine that in terms of using those formulas. So practice this, right? Practice using these general formulas that are going to work in all situations. Now, when I calculated that, I found that the mass of the electron was so small compared with the kinetic energy that was given, that the momentum worked out to be basically the same thing, 700.511. Now, I did keep additional significant figures on my calculator that are going to be important on the next line. So I'm going to come back to that. But the proton, fortunately, the momentum here is lower than the energy significantly, and that's going to help out as we move on and do more calculations. Now here's a formula. I don't know how often we've used this. We may have not used it very much. Maybe we haven't brought it up yet. But you can show that the velocity of a particle in terms of c is just the ratio of momentum to total energy. A particle's pc divided by its energy tells us what fraction of c the particle is traveling at. So this is a really handy formula because it applies to everything. And all I really need to know is what's the momentum and what's the E. Now the momentum here is just the momentum. I didn't write it that way. I wrote it as momentum squared here, but these values are just the momentum. They're not the momentum squared. So for the photon, what that would suggest is 700 divided by 700. Well, that's just a ratio of 1. And that says the photon then would be traveling at 1.00 times c, right at the speed of light. And you're thinking, yeah, of course, it's a photon, it's massless. That's going to be the case. Now the electron, we know that the electron does have mass, and that means even though these numbers are really close to each other, they're not identical. The momentum will be a little bit less than the total energy. So what I did was I just kept more significant figures for my momentum and then divided by this total energy, and I got this ratio. Now again, we might be thinking, well, can I really keep all those significant figures? And it actually works, and the reason why is there are approximation techniques where what we would be solving for here is not the actual speed in terms of c, but rather how far are we away from c. So rather than thinking of this as 1, 2, 3, 4, 5, 6, 7, 8 significant figures, you could think of that as just 2. It's just these last 2 digits are telling us how much we are short of traveling right at c. And so go ahead, you can use those numbers that you've gotten here, momentum and energy. And for the electron, yeah, it's going really fast. 0.9999973 times c. And so yes, if you got a problem like this with this much kinetic energy for the electron, I would expect that you could write that down with all the 9s and the 7.3 in it. All right, so don't just leave it at 1.00. Go ahead and use these approximation techniques, which really mean just take this ratio using all the significant digits in your calculator and you'll be fine. Now for the proton, it wasn't a big deal. Momentum over the energy is easy enough to calculate, no concerns here. And the proton is traveling at 0.820. But notice with the electron, I can't round off to 0.999. That would be very, very incorrect. This does not round to 0.999 or even 0.9999999. It rounds to something else. And so you've got to carry it out all the way to where there are not some 9s, at least a couple digits, 2 or 3 digits, where you're out beyond the 9s to see what that's going to be. All right, for the wavelength, we're going to use the general formula hc over pc. Now, notice we did not use the formula hc over energy because that's not a general formula. We have been using hc over energy for the wavelength whenever we had photons. So for a massless particle, it doesn't matter if I put, doesn't make any difference if I put pc or e in here because they're the same thing. But that's only true for a massless particle. So the general formula for wavelength is hc over pc. I got to be using pc in that denominator. So I did that for the photon, and I got 1.77 femtometers. Now, I'm using the 1240 number a lot. The HC here, for the HC, I can put my 1240 EV in. Since we're working in MeV, oh, here it is. Perfect. HC is equal to 1240 MeV femtometers. There it is. So again, it's a shortcut. It's going to save you time. Without the shortcuts, looking at this problem, I'm thinking, oh my gosh, it's going to take a half hour to do. But then when I practice using the shortcuts and use the general formulas, so I'm not searching for formulas for photons versus formulas for electrons. If I work from the general formulas and use the shortcuts, 5-10 minutes, right, to fill in, okay, 10 minutes maybe, to fill in the table. So 1.77 femtometers. Now, what's interesting here, I think, is that the momentum of the electron is almost the same momentum as the photon. And again, when we got this much kinetic energy, the electron's mass is starting to look kind of negligible. It's like, well, for this electron, its mass is only contributing a small portion of its total energy. And so what's happening here is the speed of the electron almost matches the speed of the photon. And the wavelength, to 3 significant figures, the wavelengths are going to be the same. Now, there's no concern here rounding off at 1.77. That's 3 significant figures. That's going to be enough. So I can report those as to 3 significant figures. They got the same wavelength. The electron's mass is almost negligible, so that's showing up to be very similar. Now, for the proton is not overwhelmed by this much kinetic energy. And so when I put in HC over PC on this, I end up with 0.923 femtometers. So it's traveling slower, and it's got more mass, but when I put this in, 0.923 femtometers. All right, so let's take a look at the wavelengths. The wavelengths depend on the momentum. The proton has more momentum, and it has more momentum because it has so much more mass. That's what's giving it all that extra momentum. And so it's also got a shorter wavelength. By about a factor of 2 is what we're seeing here, and that's because it has about twice as much momentum. All right, we can move on to frequency. Now, with frequency, we've got to use energy over Planck's constant. Do not use C over the wavelength. So again, C over the wavelength, that's just going to apply for photons. So we can't use those photon-specific formulas in general. These are the general formulas. If you work from these, it's going to work for everything. So if I'm going to use a formula like E over H, it's going to be handy in my notes to write down the H value in terms of EV seconds, and I even wrote it down as 10 to the minus 21 MeV seconds. Now, this is 4.15, but I think it's 4.14 to 3 significant figures. I guess I would have to go back and double check that. I'm pretty sure it comes out as 4.14. Anyway, it's close enough not to worry. And plugging into this formula and canceling out the MeV left me with 1.69 10 to the 23. Now, when I did this for the electron, same as with the wavelength, I'm getting to 3 significant figures. I'm getting the very same frequency. And that's because the total energy on the electron and the total energy on the photon are almost identical. Photons are always dominated by their kinetic energy, and the electron this time is dominated by their kinetic energy because its mass is so small in comparison. All right, so the same frequency, but the proton is going to have twice as much total energy, more than twice as much, and as a result, its frequency will be more than twice as much. That's how this works. So here are the quantum formulas built in here, calculating the wavelength and the frequency for these particles. Now, it did ask, I guess it asked at the end? Yeah, it said if we want to accelerate the electron and the proton using electric fields, using a voltage to accelerate them, how much voltage would we need? Now, the voltage that we use is going to show up as kinetic energy. And since we're working in units of EV, all I have to do is drop the E. The voltage will be equal to the kinetic energy divided by the charge. And for the electron and proton, that charge is E. And so the voltage that we would use here is 700 million volts. It's going to be the same thing for the proton and the electron. Now we can't use just voltage to speed up a photon. Photons aren't charged, and so we have to be more clever to generate photons. And it's more difficult to control the energy at which the photons are going to be generated in a reaction. But with the electrons and protons, we can use electric fields and set them at definite voltages, and that will determine how much kinetic energy they acquire. So that's a really handy way of controlling the kinetic energy of the protons or the electrons in a beam of electrons or protons. All right, let's move on to that last example, and then we'll take a break, and then we'll come back and look at another set of problems. But what we're doing here in problem 4, we're looking at a one-dimensional wave function, and here it is. So it's a different function than we've looked at before. We have looked at Gaussian wave functions. We have looked at sine functions being used as wave functions. We've looked at complex exponentials as wave functions. This is different. It's a little different. It says draw a graph of the wave functions over the region defined, and these wave functions are defined everywhere. So they extend from negative infinity to positive infinity. So draw a graph of the wave function, determine the value of the normalization constant, find the probability, determine the probability of finding the particle within a certain region. And the region that they've told us about is between x equals 0 and x equals a. Now I can look at my wave functions and see that a is a scaling factor. It's telling me how spread out the wave function is. So that'll show up on our graph. We'll make sure that that gets included. And then also, it wants us to go in and show that this really is a solution to the Schrodinger equation for a constant potential. And then it wants us to go in and determine what the energy would be for this particular wave function. All right, let's do this. And so we're over here on the right now. So here is the wave function. And the wave function, we were told, was exponentially dropping off in the positive x direction, and it also exponentially drops off in the negative x direction. So that's the wave function itself. Now that's all they told us to draw. And I put in the plus a and the minus a, and hey, it's an exponential. So by the time one scaling factor of distance, we've gone out that far, that exponential will have dropped to 37%. That's something we saw in Physics 4a when we were looking at exponential functions, and Physics 4b when we were looking at exponential functions. And yeah, the exponential functions just show up everywhere. So it's worth spending some time becoming friends with the exponential functions and being familiar with some of their properties. Now that's the probability distribution. Now I know it looks the same, that's a problem, but it's squared. So exponentials, when you square them, they just become steeper exponentials. And so this would be dropping down to a smaller number. It would be the square of 0.37, which is what? 0.16 or something. So this one's going to drop off faster. By the time we get out to minus a or plus a, the function will have dropped to, again, like, I don't know, 0.15, maybe, I'm guessing. So in part B, it says, find out, it looks like we're solving for a normalization constant. So what I can do is take the wave function from negative infinity to positive infinity. So that's sort of new. We haven't done normalizations over positive infinity to negative infinity. And so I'm going to plug that in now. That's a normalization constant that we have, and that's the wave function squared. And what I did was a familiar substitution, I hope it's familiar, of taking the argument on the exponential, 2x over a, because we squared it, and then x is equal to a over 2 times u, dx is equal to a over 2 du. And I made all those substitutions back into my wave function. So now I've got a squared, a over 2. Now what I've done here is I've said that rather than integrating from negative infinity to positive infinity, it's going to be easier just to integrate half of this and set it equal to 1/2. The wave function is clearly symmetric. It's an even function on either side of x equals 0. And so I don't need to do the integration twice. I can just do it once and set the integral equal to 1/2. So that's the plan here. Also, with this, what we can do then is make the substitutions, plug those in, and then the only derivative I have to take here is e to the minus u, and that's an easy enough integration. It's just going to become e to the minus u. And so I brought that out and set up the limits. Now, e to the minus u actually integrates to minus e to the minus u. So to eliminate the minus signs, I flipped the limits of integration. And for myself, that's a really handy way of eliminating minus signs. If minus signs start to accumulate, there's an ever-increasing chance I'm going to make an error or something. So that's a handy way to make sure that I'm not taking negative something and subtracting off a negative of something else. This way, the limits are going to stay manageable for myself. And so those are the limits of integration. At the 0 limit, that's going to become 1. And at the infinity limit, it's going to go to 0. So perfect. Everything stays positive. The a squared times 1 then is equal to the 2's canceled here. So I've got the 2 and the 1/2 canceling with the 2 here. And then I've got this has become 1. And so a squared times 1 is equal to 1 over a. I could have slipped one more line into that. I hope that the algebra should be fine. If we take a square root here, a then is equal to 1 over little a to the 1/2. That's it. That's our normalization constant. So if I use that as a normalization constant, go back and double check, I can show that the integration everywhere adds up to be 1. Now, in part C, they say, okay, fine, take the probability distribution, integrate from 0 out to a, and find out what portion of the total probability shows up within that region. So it's going to be the very same integration that we did before with different limits. The only thing changing here are going to be the limits of integration. So I'm going to say we can come back right to that step right there and replace this with 0 and a. Now when x is equal to a, u is equal to 2. And so the limits of integration here are going to become 0 to 2, and that's what we've got. And there's the integral. I'm going to evaluate it the same way. I'm going to, get the e to the minus u and flip the limits of integration. So I'm going to integrate from 0 at the higher limit. That's going to give me a 1, and then integrate to 2, which is going to give me minus e to the minus 2. All right, and this time the 1/2 that factored out did not go away, or the 1/2 that I ended up with from here. So the a squared and the a out front, those are going to cancel. We already solved for the normalization condition. So the probability here worked out to be 0.432. Okay, so this is something you should be able to do on a midterm problem. So carrying out what I'm going to claim to be a fairly straightforward normalization problem, 0.432, and then you can kind of check. Does that number make sense? I guess we should have gone through this before. If we look at the region that we're integrating, the probability region, we can see that it's less than half. That entire region from 0 out to infinity would be 1/2. If they ask me that one, I could just write it down. But if we're only integrating out to A, we're going to get something less than half. Now that's not so much less than half. It tells us that out beyond A is only about 7% of the probability. So the tails on either side are about 7%. That central region between A and minus A, that's going to be like 86% or more. All right, finally, finally, two of these items show that it's a solution to the Schrodinger equation. So they said that if we use the Schrodinger equation, treating U as a constant, so U does not have energy x dependence. It's just a constant value. So I did two derivatives. Now if I take two derivatives of that wave function, what I get back is 1 over a squared e to the minus x over a. So now this works with, I've got two separate regions I have to look at. So I can look at the region where x is positive, I can look at the region where x is negative, and it turns out in both regions I get the same second derivative. So that's useful, that the derivatives work out the same way. And then what I can do is I can plug these values back into the Schrodinger equation. When I do that, the wave functions will cancel out. Now we've seen that several times. So the wave function canceling out is really handy. It does not have to be the case. There are plenty of situations where the wave function, when I take two derivatives, I will not get the wave function back again. So, but this happens to be one based on exponentials. And so I get the wave function back again, and that often really simplifies the problem for us. So, good news, the exponential function's canceled out. And then what I can do is I can go in and write down what the energy would be from the Schrodinger equation now. And it turns out that all I'm left with are a bunch of constants, and those constants are the energy. So the energy here would be minus h bar squared over 2m, 1 over a squared plus u. And so that's what I wrote down for the energy. So I just rewrote that energy formula. So it's going to depend on what A is equal to. The energy that we have here is negative, which is interesting. And everything we've done here works. There is one complication that we haven't talked about, so let's talk about that. And that is that I got a wave function with a discontinuity in it. Up until now, we've always seen wave functions that are smooth functions of x. But this one has a discontinuity in the first derivative. So there's that peak at the center, but when I take first and second derivatives, the first and second derivatives exist everywhere except right at the peak. And right at the peak, the derivatives do not exist. Now, what happens, what we can show, is that sudden discontinuity means right at x equals 0, right where the discontinuity occurs, there is a very narrow and very deep potential energy function. So we've kind of ignored that. We've said that the potential energy is 0 everywhere. But now we have to put in a modification to that. Well, in reality, the potential energy is constant everywhere except right at x equals 0, and there's a very deep potential energy right there. So it's a very short-range force holding something in place. Maybe it's a nuclear force that we're modeling. In any case, that one really deep potential energy well is creating a quantum state. So there is a quantum state, and it's negative, and that negative energy says that there is a particle that potentially could be confined to that narrow region, and it would have this much energy for the particle. Okay. Another way of thinking about this, if you remember, there was that non-infinite potential. So the potential that exists here would be finite. Its depth would be finite. And what we're looking at are the exponential drop-offs on either side of the well. So we will have one quantum state, and it will have this energy to it. Okay. So good problem. I mean, this is kind of chapter 38 stuff. We're looking at utilizing the Schrodinger equation. They've told us that the potential energy we can treat as a constant. They've given us the wave functions, and they've asked us to draw the pictures, normalize the wave functions, calculate some probabilities, show that the wave function is a solution to the Schrodinger equation, and then finally solve for what the energy would be. All right. Okay, let's take a break. That's a good place to stop, and we'll come back and look at the next set of practice problems that we have for the upcoming midterm.